Let's look at how to find all of the zeros of the polynomial function f of x equals 6x cubed minus x squared minus 11x plus 6. So let's review the steps that we can use to help us find some potential zeros to work with and an interval to focus on. So I'm going to start by finding Cauchy's bound. This helps me when I go to graph on my calculator just to be able to know where to focus in to find where my real zeros are. So we want to pick out two numbers from our function. One is going to be what we call m. This is our largest coefficient. We'll just take the absolute value, so 11 is the largest coefficient. And the other number that we need is the leading coefficient. So for this function, that is 6. So using our formula for the bound, we're going to take the opposite of 11 over 6 minus 1, and then 11 over 6 plus 1. So if we simplify that 11/6 minus 1, we end up with negative 17/6 to positive 17/6. So it's just a little bit less than negative 3 to positive 3. Next, I'm going to use my rational roots theorem. So what this does is it gives me a list of potential zeros. So we're going to make a list first of what we call p. This p comes from the constant term of our function, which in ours is that 6 at the end. So we want to make a list of all of the factors of 6. So they could be either positive or negative. So positive or negative 1, positive or negative 2, 3, or 6. Those are all the numbers that divide into 6. Then we're going to make a list of values for q. This comes from the leading coefficient. So that's also 6. So it's going to be the same list this time. So we use the constant and then we use the leading coefficient. So now I'm going to make a list of possible values for p over q. So what I'm going to do is I'm going to take and I'm going to divide each of my values of p by my possible values of q. So I'm going to start with 1 divided by 1, 1 divided by 2, 1 divided by 3, and 1 divided by 6. So 1 divided by 1 is 1, 1 divided by 2 is 1/2, 1 divided by 3 is 1/3, 1 divided by 6 is 1/6. So now I'm going to repeat that process, only now I'm going to take 2 and divide by 1, 2 divided by 2, 2 divided by 3, and 2 divided by 6. So 2 divided by 1 is 2. 2 divided by 2, if we reduce that, is 1. I've already got that in my list, so I'm going to skip over that. 2 divided by 3 is 2/3. 2 divided by 6, if I reduce that, is 1/3. I've already got that in my list. Let's do it again. 3 divided by 1, divided by 2, divided by 3, and divided by 6. So 3 divided by 1 is 3. 3 divided by 2. 3 divided by 3 is 1. We've already got that in our list. And 3 divided by 6 is 1/2. We've already got that in our list. So one last time, 6 divided by each of our values of q. So 6 divided by 1 is 6. 6 divided by 2 is 3. We've already got that. 6 divided by 3 is 2. We've already got that. And 6 divided by 6 is 1. So what we have here, so 1, 2, 3, 4, 5, 6, 7, 8, 9 values, but with plus or minus. This is a list of 18 potential zeros. So they're not all going to be zeros, but in that list, if we have any rational zeros of this function, they're going to be in this list. So this gives me some values to look for when I take a look at my graph. So now what we want to do is we want to graph our function on our calculator. One of the key things is that we're going to set our window so that the x minimum is negative 17/6 and the x maximum is positive 17/6. Let's take a look at what that will look like. So here's what we'll see on our calculator screen. So in my y equals button, under y1, I'm going to put my original function. In my window settings, I'm going to change the x min and the x max. So that's our negative 17/6 and our positive 17/6. After you type that in your calculator, we'll change it over to a decimal and then hit graph. So when we hit our graph button, we'll see that it appears that there are 3 horizontal intercepts on this function. I usually look to see if there's any at integer values first, those whole numbers that are a little bit easier to work with. And when I look at my graph, this one right here looks like it's at an x value of 1. 1 is one of the values that we had in our list of p over q, so I'm going to use that as my 0 to get me started. So if my 0 is at x equals 1, what I'm going to do is I'm going to use 1 in my synthetic division. So I have 6, negative 1, negative 11, and 6. So bring down the 6, multiply, and then add. Multiply 1 times 5, and then add. Multiply, and then add. So we got a remainder of 0, which means that it really is a 0. And what we have found is our original function. Since we were dividing out the 0 with x equals 1, the factor that goes with that is x minus 1. And then now the quotient that came out of our synthetic division gives us 6x squared plus 5x minus 6. So we know that one of the zeros of our function is x equals 1. The others appear to be some kind of fractional values or something in between those integers. We can find those by looking at our quotient and solving when is 6x squared plus 5x minus 6 equal to 0. This is one that can be solved by factoring, but there's a little bit more trial and error involved than some. So let's look at how we could use our quadratic formula to solve as well. So thinking about our a, our b, and our c, we're going to start with the opposite of b, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Now come back through and simplify. So underneath our radical, 5 squared is 25 minus a negative, so it's going to be plus 4 times 6 is 144 all over 12. So we can simplify under the radical further. If we add 25 and 144, we have 169, still all over 12. It turns out the square root of 169, that's a perfect square. 13 times 13 is 169. So the square root of 169 is 13 all over 12. So actually consider each of those separately, the plus and the minus. So negative 5 plus 13 over 12 and negative 5 minus 13 all over 12. So end up with negative 5 plus 13, we have 8 over 12, which we can reduce to 2/3. Negative 5 minus 13, we have negative 18 over 12, which we can simplify to negative 3/2. So what we have found is that the zeros of our original polynomial function, there's 3 of them, x equals 1, x equals 2/3, and x equals negative 3/2. So those 3 horizontal intercepts correspond to 3 real zeros.